Hello everybody, this is Nimmi Damodaran with Apt Associates based in the United States. Welcome to Terry's webinar series on improving solid waste management. As many of you may know, Terry is a regional implementer of the UN Climate and Clean Air Coalition Municipal Solid Waste Initiative. This initiative seeks to reduce emissions of methane and black carbon from the waste sector. Methane is primarily emitted at landfills, and black carbon is from burning waste. Today we have with us David Fisher of SCS Engineers to talk about methane monitoring and landfill fires. David is a California-based environmental scientist specializing in solid waste management for the last 23 years. He has worked on projects for some of the largest landfills in North America, and he is currently the National Compliance and Quality Control Manager for Operations Monitoring and Maintenance Group at SCS Engineers. At SCS, he helps manage environmental monitoring and control systems on over 300 facilities. Through his work, David has learned the importance of using monitoring data to guide the facility operations and to demonstrate good environmental stewardship. So I'm going to hand over the presentation to David, but before that, I would like to mention, as Ashish mentioned before, if you have questions, please enter it in the chat session, and I will monitor your questions. And if there are clarification questions, I will interrupt David, or otherwise we will keep questions and answers to the end. Thank you very much. David, please go ahead.
Thank you, Nimmi. And thank you, Climate and Clean Air Coalition and the Energy and Resource Institute and App Associates for having me. As well as thank you all participants for taking the time out to learn a little bit more about fire and odor management at solid waste disposal operations. Namaste. Today we're going to talk about surface fires and subsurface fires, and with that definitely comes the ideas and practices of cover and compaction. And through all those, we'll be discussing monitoring and controlling of fires and odors. I'm here to share with you guys some of the things that I've learned throughout my time as an environmental scientist working on solid waste facilities, and as well as a general practitioner. With my audience in mind, most of you guys from India, the home of yoga. I believe you guys should, know, like what the yogis know, that, when you talk about fire, the first thing that might come to mind is breath. It is as we breathe in oxygen, we oxidize it, and that helps our bodies continue to energize and respirate and sustain life. So with that, we could actually start this meeting with a deep breath in and synchronize our breath actually halfway across the world, which is about as far as anyone can get or hope to get. So thank you guys, and I hope you enjoy our presentations. I believe you can chat questions as they arise, and Nimmi will moderate those, and we can have hopefully a fruitful discussion. So let's start with the basics here. The original idea was the fire triangle needing three things: oxygen, heat, and fuel. In newer fire science, they teach the fire tetrahedron, which adds the additional information of the chain reaction. And what that adds is the idea that, yes, you can, if you have the main three elements, oxygen, heat, and fuel, which would normally sustain a fire, you also need the interaction between those three. So if, for example, the fuel was covered with a fire retardant, it would actually prevent the fire reaction even though heat and oxygen were present. But yeah, even more basic than that, we see the picture of a fire on the left, and this is the shape we call these typically, like a TP fire. But that shape should also remind you of something else, and that something else is the solid waste facility pyramid or large mound. And you could think of the sticks as a potential fuel source inside that mound, and the space between the sticks as room for oxygen. So you really have all, once you add heat, you have all the elements necessary for a good, fast, rapid oxidation, also known as a fire. To the right of that picture, you'll see a square top battery, 9 volt, and it's touched to steel wool. And what happens there is it pushes electricity through very thin pieces of steel wool, and it heats up the steel wool. The mass of the steel wool in those thin shredded format, it doesn't allow it to release the heat, and therefore it gets real hot real quick and actually catches on fire. It's an example of where shredded steel, you wouldn't think of steel as being combustible, is actually combustible. Okay, so we have all those oxygen potentially present in a landfill. Of course, fuel, any carbon-based material would serve as a form of fuel. And then even, as you see oxidized material such as metal in the right state can serve as fuel. You could have additional compounds such as industrial compounds as liquid free product like gasoline or petrol. And then heat, as we'll discuss, is actually present in the landfill due to biological decomposition, the heat from that process. And all those together, without any flame retardants in any appreciable amounts in the landfill, allow the opportunity or the potential for a fire to start. Now, what I want you to focus in on is the one part of the fire tetrahedron. The main one that we can control is actually oxygen, because fuel is always going to be there. The chain reaction or potential for the chain reaction is always going to be there, and the heat will always be there. It's the oxygen portion that we can affect through proper solid waste management. So 2 types of landfill fires, the subsurface and the surface. So as you would think, the subsurface is coming, is happening inside the fill and often not noticed at all. But in this case, in the picture on the slide picture on the left, you see evidence, physical evidence of combustion. And we call that subsurface oxidation, typically out here in the West, or also known as SSO, the acronym SSO. And on the right, we have a surface fire. So you can see that potentially one or more of the pieces of the refuse that made it to the facility most likely was the source of ignition, or the original heat, and it was enough to start the fire on the surface. Now, what I'd like you to focus in on this slide is the interaction between the two, where a subsurface fire, as you could imagine, could eventually burn to the surface and catch surface material on fire and create a surface fire. Now, likewise, the opposite is true. A surface fire can burn voraciously enough to actually heat up the waste mass and find a crack or a fissure or a way into the waste mass and start and ignite a subsurface fire. Now, as I mentioned the previous slide, surface fires are usually a result from an offsite source, such as a hot load. That is a term that means a load comes in with, for example, some coals, some embers, perhaps from a barbecue, a fire, little ashes and the coals from a cooking fire. Now, it also can be from a piece of equipment. So, for example, maybe some of the customers that come to visit the facility to use the facility perhaps don't have a functioning spark arrestor on their vehicle. Smoking, of course, can be another source. Waste salvagers or scavengers, we'll talk about that in a little bit, can be another source. Mowers is one that's happened in my experience at a site that I used to work on, where we had actually every season mow down the grass to actually create a fire break around the facility, and the mower that was being used hit a rock and made a spark and ignited the grass, and the grass burned the surface of the landfill, including the appurtenances such as the landfill gas system, which is often on the West Coast, above ground, and melted the pipes. I have a couple of pictures of that later. Compost piles is a special one that we see have a high potential to create a surface fire as they start decomposing and creating heat on site. They're not buried in the landfill; they're a pile on top, waiting to be processed. But in that process of waiting to be ground up into a nice fine material that would not hold air or allow as much air to infiltrate, they sit more like the teepee fire slide, heat up, and potentially combust. And then, of course, off-site brush fires can lead to on-site fires. Now, the picture you see here on the right is from this year, actually, in the States, in Colorado, at a transfer station facility, from one of the largest commercial solid waste disposal operation in America. And you can see that, so I guess my point is, one, these happen. This is not something that happens necessarily in the past. Even in the States, we're still having to manage fires. And you can see in this next slide that even with the use of modern technology and access to copious or sufficient amounts of water, you can tell that the building wasn't gonna last through this fire. The whole thing was consumed by the blaze. Luckily, nobody was hurt, but you can see that once a fire starts in these conditions, it is very difficult, to say the least, to control or put out. Okay, so a little bit more on hot loads. We talked about brush, leaves, construction debris, fireplace coals, burn barrel residue. And then in this slide, I put tires in there as a special waste. Now, in the States, we actually do not accept tires in the landfill. They're all segregated before the landfill, and they're either A, recycled here, or more likely, they're shipped out of the state. And it's to the tune of about 1,000 tons a day. So they're shipped out of state, often to other countries to use as a fuel source. And so we don't have to deal with them in our solid waste facility, but of course other people do. And we are on the landfill, we're appreciative that we don't have to deal with them because, one, you can see they're highly combustible, and two, they're really hard to compact. So once you try to cover them over with dirt, they want to spring back up into full form and create an air pocket. And that air pocket can lead to air infiltration into the solid waste mass, which can help set the stage for an SSO, subsurface oxidation event. Now, if a hot load hits your facility, or arrives at your facility, typically, I think the point for this is the first thing you do is not to, what you might think, start spraying it with water. The first thing you try to do is, one, isolate the load from all other combustible material. Hopefully, you have a place to move it to that's away from all the rest of the refuse. And then two, start separating the fire, trying to cut the fire away from the fuel source. And luckily for solid waste facility operators, they have a fair amount of what we call yellow iron, heavy equipment. And it's usually just enough to do the job, to separate it out, compact it, and then, of course, after the fire's all out, you'll want to wet it, right, to make sure there's no lasting embers, and compact it and cover it. And a theme for this presentation will be and compact it again. And I'll probably say compaction probably another 30 times before we're done here in the next 30 minutes. Now, surface fires can also be, equipment related, as mentioned earlier. And here's a good picture, kind of illustrating that there's not much compaction going on here. This is a dozer. Dozers are meant to push trash more so than they're meant to compact trash. So it's good to push trash into the right location and then have a specialized waste compactor compact it. But, with all this loose refuse, you can see how could be a potential for it to get up into the equipment, engine area, exhaust area, high temperature area, and potentially be a source of ignition. Likewise, if you are maintaining your equipment, you might be welding it. Welding is a notorious source, obviously, of ignition, and usually requires an additional person called a fire watch. You have the welder focusing on the welding, and then you have a secondary person who is designated as the fire watch, making sure nothing catches on fire, and of course they're equipped with proper fire extinguishing equipment in case a fire does arise. Now, waste pickers and scavengers, present a special condition and consideration at facilities because, even in the States here, back in the 1960s, this is how it was done. We brought the waste to, we call it the table, the area that's designated for disposal. And at the table, it would be ignited. All the combustible material would combust. And it would leave all the metals and salvageable material to be easily sorted through and pushed off to the side for recycling. And it wasn't until the concerns, the air concerns of the associated pollution with the combustion, it wasn't until after that we started not combusting it on site and compacting it and covering it. So you're going to want to control surface fires, you're going to want to limit access to the working phase. Obviously from as I described, from a fire standpoint, but also from a human health and safety standpoint. The yellow iron, the heavy equipment, is not forgiving and doesn't mix well with a bunch of human traffic, on the table, on the landfill working phase. I guess the only thing that people have going for them is that they sometimes can be faster than the slow-moving dozer. But of course, in the midst of a bunch of debris, it's easy to trip and fall and and not be seen by the equipment operators. Okay, so subsurface fires now. We talked about surface, and now we're going to go down subsurface. Typically, as I mentioned, a result from air infiltration into the waste mass. And when you see the word air, you should also be thinking oxygen. Fire is below the surface, and when it is, as you can kind of see in this case, it would be much more difficult to extinguish. A surface fire, you can actually see the flames, you can see the fuel, and you have an ability to and a more logical method to extinguish it. But as soon as it's in this pile of dirt and concrete mixed with lumber and construction debris, it's much more difficult to extinguish. So you need to know the signs of an SSO, subsurface oxidation event. And we'll talk about those in the following slides. A little more on the fire tetrahedron fuel, right? You guys got this. You already know this intuitively. There's fuel there. There's nothing we can do about it. We've been taking it for years. Yes, it will slowly degrade. And it's actually a benefit of the old days when they used to burn it right on the table at the disposal phase, because it would quickly degrade the fuel source. So after they pulled out the metal and then pushed that residual ash, there was a lower chance that it would combust and decompose. So in that sense, the old way actually made it less likely that there would be a fire, because, or at least an uncontrolled SSO, because all the fire happened on the front end of the process. Now we need to add another thing here, and which is not just the solid fuel like wood. Landfill gas can serve as a fuel, as the organic material with carbon in it breaks down. It's going to produce methane, and it only does it under certain circumstances, which is anaerobic decomposition without air. And we'll talk about that a little more as well. Heat, and this is kind of how we step into it, the heat part, because we said the heat's already present. Well, how did it get there? If you're landfilling in the winter when it's cool, well, how does the waste heat up? Well, anything that with carbon in it is going to be subject to microbial activity, and you have these microbes, different microbe populations that kind of stratify themselves into thriving in different conditions. One of the conditions is temperature. Is chronophilic, mesophilic, and thermophilic are microbe populations that stratify themselves associated with temperature. But there's another stratification, and we don't go into it too much detail, but it's the aerobic, as in microbes that thrive in the presence of air, and anaerobic, microbes that thrive in the presence of no oxygen. And it's those anaerobic bacteria, anaerobic microbes, that produce the methane. And it really is, the natural state of a solid waste mass, where, it is compacted, pushing out the air. The natural state is to promote anaerobic decomposition. Now, the reason why two reasons why we as a landfill operator and scientist, we like to, favor and proliferate anaerobic decomposition is because they don't get quite as hot as aerobic, the air loving bacteria. So they're not producing as much heat. And two, they produce actually a valuable fuel, landfill gas. So as you can see here, yeah, heat levels range according to waste types and age. The more organic material, the more decomposition you're going to have. The younger the material, typically, the more decomposition you'll have, and with age, as things decompose, you'll have less activity. Wood combustion, this is kind of here taking it full circle from decomposition to a fire. You can see where thermophilic operate and thrive in a range of 35 to 75 degrees C. You can see there's a near crossover or a close association between going from 75 to the 80s. And as soon as that temperature does get that high, usually in the presence of the aerobic bacteria, the air-loving bacteria, the temperatures can rise and get into the wood combustion range. And as soon as the wood starts combusting, it's creating a little more heat, and that can drive it into wood debris, construction debris, auto ignition temperature ranges. And at that stage, as you can imagine, and probably potentially have experienced, now the thing is a sustaining reaction. And once you have a sustaining reaction inside of a landfill, you have very, very few options available to you to manage it. Okay, so to the air. This is, as we remember in the fire tetrahedron, the oxygen is the primary part of the fire tetrahedron that we can control. Now, the picture on the right, is actually a well casing, so a landfill gas well casing. So a hole was drilled into the landfill, and a pipe, a PVC casing in this instance, was dropped down maybe 100 to actually up to 300 feet now into the landfill, and surrounded by gravel. And you can see here that things didn't quite go right because there's a void right next to it, and those voids can happen from natural settlement, but they can also happen, as we'll see here in the subsequent slide, that it can happen because once you start pulling the landfill gas out of the landfill, you pull too aggressively, and you actually end up pulling in the atmosphere into the landfill, including oxygen, and potentially starting a heat reaction, and can result in an SSO event. Okay, so here's a diagram to help describe this. Now, you see a well here, as I just described, but you can also think of this as void space. The well, it obviously can represent a landfill gas extraction well, but even a site without any landfill gas extraction wells can have void spaces, especially when compaction the compaction density isn't very high. But this kind of illustrates what can happen with oxygen in the landfill, which can be caused from extraction of landfill gas. Normal extraction, put some vacuum on the well, start pulling out your gas. It's up at the top, hopefully you can see it, 1 inch of vacuum, and 5 CFM of flow, and 57% methane. 0 oxygen, and zero balance gas, which actually is a term for nitrogen for all practical purposes. And that's what you would expect. There's methane in there due to anaerobic decomposition, which produces methane and CO2. You pull a little more, you can see the radius of influence kind of pushes out away from the well. But yet, you can see the flow increasing and the methane still stable. Basically, the gas composition the same. And it's not until you keep pulling so much CFM where the radius of influence goes outside of the waste mass. Now that can happen on the sides, but more likely it's going to happen right at the top of the casing of the well. And at that point, you can see the methane starts dropping, the oxygen starts climbing, and the balance gas or nitrogen starts climbing as well. Now, so this is when you're measuring what's inside the landfill through, a sample port. This is what you'd be looking for as far as evidence of overpulling, which is going to start reducing the anaerobic bacteria and allowing the aerobic bacteria to thrive more, creating more heat and increasing the risk of an SSO. Now, one thing to know if you think about chemistry and you think about aerobic bacteria consume oxygen. So as you start pulling in oxygen, it actually takes a while for oxygen to show up at all. The first thing you're going to see is the balance gas. And the reason is because nitrogen is an inert gas. So when it gets pulled into the landfill, nothing eats or consumes nitrogen. It just passes through. So balanced gas or nitrogen is actually the first gas constituent that you're going to see that changes to allow you to see an indication of overpull. Now, as far as fires go, you can see that once something starts, and it starts creating an avenue, a channel through the waste mass. If you think of the mountain as the waste mass, and the line of fire, creating an avenue somehow through that waste mass, against many odds, because due to compaction. But for example, say you had a part of the waste mass sheared off, sloughed off, it's going to create a nice channel, a fissure, a crack that could function as a channel for oxygen to go from the bottom of the fill to the top of the fill. And it's driven by the thermal gradient of the SSO, subsurface oxidation event or fire. We actually really stay away from the fire word in the States. We always say SSO. It's an industry thing. But that's what can kind of see how it can start driving and continue the growth of the SSO. Now, what do they look like? Well, if you're lucky, they look just like this. No flames, no smoke, no odor. It's just kind of a depression in your site, which, in this case, it looks like it's, holding liquid, and that could help, cool down the fire. But you remember the liquid, thinking a little bit more about decomposition, those microbes, anaerobic and aerobic, they need a certain amount of moisture to really kick into gear. And it's actually, potentially the depression is going to actually funnel more moisture into this SSO area, which could actually drive the reaction. Sure, cracking, especially rapid cracking, rapid settlement, couldn't be a sign that you're looking for of an SSO. But also, you could think of geological stability and potentially shearing of a waste mass. This is, these are big signs where you'd be thinking, well, shoot, I need to get some heavy equipment, some yellow iron on here, and get this recompacted the best we can. Again, this one's pretty obvious, right? Because unlike the previous two, now you got real physical signs, where there's smoke, as they say, there's often fire. And again, in this slide as well, the one thing I'd note in this slide is if you see all these metal casings, as if maybe they were structural piers for maybe some type of structure, maybe was the idea to put them on, to build on top of. Now, this is kind of reminds me of a vertical landfill gas extraction well, where, somebody, hammering these in, the caissons, I believe, typically they're called, could actually create, a space, an avenue, putting holes in the waste mass, which could allow oxygen to enter into the fill. So yeah, use your senses, sight, smell, and touch. Here's two pictures of the landfill gas wells where they got so hot they actually burned. So you're looking for the wrinkly plastic and smelling for it as well, any different odors associated with that aren't typical. The other thing you could be looking for is staining. So if you see a crack, that's one thing. If you see a crack with steam coming out, that's another thing. If you just see a crack with actual maybe a residue around it, that could be a sign that it's a little more than steam. It actually could be bringing up partial combustion products like smoke and staining the cover. Okay, so now we get to move on to prevention and control and monitoring. And Nimmi, if you have any burning questions out there, we can always field those as well. No pun intended.
Actually, there's actually a very relevant question just as you're going into this, David. So, there's a question that this type of condition and problem exists in every country. So if it's so dangerous, how do you manage the different types of solid waste without fires? But I think that's where you're getting in right now as to how to manage it and avoid fires. Am I right?
Yes, that's a great question and a transitional question into our next topic. But yeah, I mean, think about it. Humankind has been, actually, blessed and cursed with fires all at the same time. And they all kind of end up at our gate, right? As we recycle more, we're extracting a lot of material. Hopefully, some of that material is, like wood debris that can be composted, and tires. These types of debris, source separated out on the front end can reduce the chance of having to deal with fire. So I'm gonna get to really I want to focus on prevention a lot, just because once it happens, it really is a site by site basis, in most occurrences, very few options, and it usually takes a fair amount of time and expense and energy to really control it. I mean, that's usually your best. I mean, it's usually where it ends up being, and just controlling it. And in some cases, eventually, then it does go, it does die down enough to really not be noticeable. But in many cases, I'd say in most cases, it's never necessarily 100% out. And that's why, we'll focus on prevention a lot by limiting air and oxygen intrusion. And here we go, compact and cover. And we'll go into this a little more detail. And then monitoring, doing physical observations on your site. So if you're not going out to the, as we say in the States, the back 40, which means kind of the parts of the site where you aren't really working, you're not going out to the back 40, you're going to be missing opportunities to catch some of these things early, and also identify things that should be maintained, such as fire breaks around your facility and cover cracking. Speaking of cover, maintain cover on closed portions of the site, and then balance your landfill gas system. And that just means if you do have a landfill gas system, you want to remove the gas so it doesn't either escape through the cover and create air pollution, or escape subsurface laterally off-site and potentially end up in somebody's residence. But you don't want to pull it so much that you actually bring oxygen into the landfill. And then, yeah, real fundamental stuff, easy stuff to do, checking temperatures on different waste piles and oxygen readings regularly. Okay, cover. Now, here's my take-home point. And I've seen a few slides where it seems like the site is really cover-rich. They're using cover, but they're not. It doesn't seem like they're compacting. And they really go hand in hand. Compaction is number one. Even if I had to choose, I would be choosing compaction over cover. And the reason is because I'd be pushing all the air out. I'd be smashing things flat and not leaving air voids, and that alone reduces the ability for fire to spread. It's actually pretty darn hard for a fire to spread on a well compacted face. And also, once that's done, it makes it a lot easier to apply cover, and you use a lot less. And as you can imagine, if you don't compact, and then as soon as you put dirt on it, the cover's just going to sift through the waste, and you'll lose all your cover down in the waste. The figure 2 on the right here also says, you got to do it. It has to be a daily practice. You can't say, "Oh, I'll catch up." There is no catching up for the most part. The graph shows that if you compact in 2-foot lifts and really thin lifts, you can just do 3 to 5 passes and get up into well over 1,000 in this case pounds per cubic yard. However, as you let your lift depth increase up to 10 feet or about 3 meters, your ability to compact that lift is severely reduced. And you can run your compactor on it all day, and it just compacts the very top layer and leaves the lower layer uncompacted. So I throw this out here. I mean, so what? So what if you have an uncompacted landfill? What's your choice? Here's the extreme choice. It's called dynamic compaction, and it's just dropping a weight. You're trying to do, force, over a short period of time is really going to punch down that waste. As you can imagine, this could be pretty impractical. Now, there's some actually pretty creative ideas, associated with improving compaction, where some operators will actually add a large soil stockpile, and that can surcharge the waste down. Now, you could end up with some geotechnical concerns associated with a large stockpile, especially near the edge of a slope. But throw that out there is that you can think of other ways besides using a rig, a dynamic compaction rig. Now, there's one other way that to some degree works, is where if you queue your haul route, all the folks bringing in waste to your site, you actually use the weight of their vehicles, and they don't like it too much. But if you send them on a circuitous route, kind of a long way around, they're actually helping compact the waste. All right, so daily cover, you got, in addition to fire, daily cover does wonders for your short-term operation and your long-term operation. Fires, of course, reduces odors, controls vectors and rodents, and reduces stormwater infiltration and reduces litter. So we can talk about that more as we go if you have questions on it.
David?
Yes?
You have about less than 15 minutes, just giving you a time reminder.
Okay, thank you, Nimmi. I'll speed it up here. And of course, the the cover can also help control, unregulated or unmanaged scavenging and recycling, and then of course help not only the immediate stuff, but the long-term solid waste maintenance, improve that as well. And once you put it on, sometimes you can strip it off, and that can save airspace. And you can use, if you have a good stockpile of soil, you could use that. Typically they'll use a scraper to haul it. And the 15-centimeter lifts, about 6 inches. Kind of the reason for that is it helps, reduce stormwater, but it also is typically they've measured it as, the minimum thickness to prevent insect larvae from crawling through and hatching out into the environment. But you don't have to just use soil. You can use a whole bunch of stuff. Shredded tires, however, the caution could be that then they might be more prone to a surface fire. Ash and residue, great. Yeah, if you have those, that can be a great, source of cover. I guess you could have a hazard associated with dust, so you got to be careful there. Shredded C&D, and they say not wallboard because it has a whole bunch of sulfur in it that can lead to hydrogen sulfide, which can lead to odors. But most popular often is tarps, which are, we actually saw a picture earlier, a tarp, it's just a thin tarp. And then, of course, once you have your cover, you're going to have to maintain it over the long haul, and that helps reduce oxygen and reduce liquid infiltration. And then as you manage, you got to always think safety first. Here's one of the SCS are out here, one of the SCS engineer field technicians out at a site in Nevada, and he's monitoring a well, and right on his shirt pocket he has this 4-gas meter, and it's measuring H2S, which is a toxic and flammable gas, carbon monoxide, which is toxic, the LEL, lower explosive limit, so for methane, and then the oxygen. So these are things. It's a nice little tool. It costs about $600. That can be used when you're out there monitoring. It can keep you safe and keep your team safe. And then confirming carbon fire through carbon monoxide testing, and that can be done relatively inexpensively. The previous picture had our technician with a gas emission monitor that monitors all this stuff, and he can make about 60 readings a day and measure all these things. It's not something you have to take out to a laboratory. Of course, you get the ability to identify oxygen sources and then cut off the oxygen supply typically through compaction. And then more management pictures. So you can see here on the left, there was probably a combination, a surface fire and a subsurface fire. So water, you're going to need to apply water to manage surface fires typically, but you don't necessarily think it's going to control subsurface fires because, one, the water's not getting there. It's going to evaporate long before it gets deep into the waste mass, and any moisture that does get there probably is just going to help accelerate decomposition and potentially heat. And then on the right, the heavy equipment, yellow iron, maybe just get out there and dig it out, and I know that can be hazardous, and you might need several pieces of equipment, but that is, digging it out and getting to the source and compacting it, recompacting it as you go. Of course, there's, if you look at it, some folks were going to be doing direct push probes, a geotechnical push probe into the waste, using a lot of force, and then pushing in like carbon dioxide into it, or liquid carbon dioxide to cool it and remove the oxygen. Here's a shot of some monitoring equipment, the Draeger tube, and these are like $15, or I guess it's 1,000 rupees per tube, and then a tunable dial laser, which we really like because you don't have to calibrate it on site, and that measures not only down to the part per million methane, but it also measures up to the 100%, so full scale, low level detection to high level detection. And then temperature can be pretty easily accessed through a temperature thermometer, and these non-contact laser thermometers are relatively inexpensive. And then if you want to get fancy, you can do thermal imaging. They have planes actually that with a thermal imaging camera that fly over and can detect hot spots on your facility. And then as far as odor management, this is actually the state of the art. And if you really want to dig into it, you got to check out the odor emissions from MSW sites from the CPCB right there in India, and that's very detailed and very good information on how to set up a program to follow your nose, so to speak, and use a nasal ranger in this case, where it dilutes your facility gases or your ambient air with purified gas that runs through a carbon filter that would take out all odors, and then you kind of adjust the mixing ratio to figure out when you can smell it, and then from there you can calculate how far the odors travel off your facility. And with that, you're going to want to keep a track on your meteorological data, your wind, your temperature, wind direction, rainfall, and you can also take grab samples and send those off-site for an additional analysis. And that takes me to the end